Okay, so anyway, pH was proposed by this great name Sorensen as a convenient convention. So pH then refers to, the P stands for power, the power of the hydrogen ion concentration. And power is ultimately important in this because it's the power that's on the values of 10 that then ultimately, when you get the logarithm, etc., become the values that are the pH scale. So in any case, pH is negative. It's a negative of the logarithm of the the hydrogen ion concentration, and pH is equal to minus log of H3O plus. So I mean, that's the way it's written. This is the hydrogen ion concentration again, and this is the mathematical way to work it out. Low value of pH corresponds to a high concentration. Okay, so this is one of the key things on this. A concentration of 10 to the minus 7 ends up being a pH of 7 or thereabouts. As opposed to if you have a higher concentration. Now remember, these are negative powers, indices. 10 to the minus 7 is one concentration. If I take a higher concentration, then that would be 10 to the minus 6, and a higher than that would be 10 to the minus 5, and then 10 to the minus 4. But when you get each of these and work out the minus, the log of them, 10 to the minus 5 it turns out to be 5. 10 to the minus 4 turns out to be 4. 10 to the minus 3 turns out to be 3. So as the concentration gets higher in the 10 to the minus 4, 10 to the minus 3, etc., the pH value is lower. So therefore, look at a low pH number corresponds to a high concentration. That's what you've got to remember. Okay, so there you see it. A high hydrogen concentration refers to a low pH, and that's exactly what we said there. And bases work basically in the same way too. Okay, so a mathematical question then, always great to highlight these points. Hydrogen ion concentration is given. Hydrogen ion concentration is 0.00015 molar. Okay, so this is given. That's given. Okay, so in our pH formula, this value is given. Do a sub right in here. Okay, so just type the value into your calculator, press the engineering button, and you get 1.5 by, well, in actual fact it'll be 10 to the minus 3. We won't talk about that in any case, but look at 1.5 by 10 to the minus 4 corresponds to 1.5, decimal point will be there. How many hops is that? 1, 2, 3, 4. So there's your negative 4 right there. Okay, in any case, do a plug and chug in the calculator. pH is equal to 3.82. That's the answer. Next problem, calculate the hydrogen ion concentration of a solution. This time you're given the pH, so you're given the lefty. You're given 2.19 for the lefty. Right there, 2.19, and you need to work out the insides of the brackets, the hydrogen ion concentration. So basically it's a case of switching sides, the negative log. That's what we need to do. So the negative goes first, and here you have it right here, negative 2.19. We've still got the log on the left, log of hydrogen ion concentration. To get H3O, you've got to do an anti-log as per usual for this. When you switch sides, you've got to do the inverse. And the anti-log of minus 2.19 is your hydrogen ion concentration, 6.5 by 10 to the minus 3. Now, this 10 to the minus 3 is a higher concentration than this one here, which was 10 to the minus 4. Don't be put off by the 4 and the 3. That's the point about this. The negatives actually are the opposite. That's a lower concentration at minus 4 in the power. This is a higher concentration at minus 3. You do the exact same thing for the POH. Here's a problem. At 2.8 by 10 to the minus 3 molar NaOH, it's a strong base. Strong bases mean full dissociation. So you're going to get whatever the molarity of the NaOH is, the concentration of the OH minus is going to be the exact same, and you see it's identical. Okay, so in our formula, POH equals minus log, and we just do a direct sub in, 2.8 by 10 to the minus 3, plug and chug, POH equals 2.55. So again, I suppose it's always good to summarize and make sense of all of an overarching view of all this. pH and POH. So the pKw equals, okay, so the P value for the dissociation constant for water is equal to pH and pOH, which is equal to 14. Now remember what that is. If you go backtrack, you'll see the hydrogen ion concentration is 1 by 10 to the minus 7. OH concentration is 1 by 10 to the minus 7. Do the P's on both of them, minus log of both of them, and you will get 7 and 7. So that's where your 14 comes from right there. In pure water, pH and pOH equals 7, neutral solution. We all know that. pH scale, always good to have a look. At 0, you see right here, mostly it's all acidic. 7 is neutral, that's what water is, and basic is up at the 14s, okay? Now remember, it's a logarithmic scale, so that means that the difference between 0 and 1 corresponds to a power of 1, and 10 to the power of 1 is 10, so this is 10 times greater than this, approx. 10 squared is 100, okay? So this is, again, logarithmic means that we're working out the index. 2 is an index. 10 squared is 100. So this figure here is 100 times more than this. Okay, in concentration. That'd be the idea there. Okay, and keep going like that. That's the idea. Did I just say more than? Less than, okay? So remember that these come originally from powers of minus 1s, minus 2s, minus 3s, minus 4s, minus 5s in concentration. So therefore, this one would be a minus 1 in concentration. When you get the pH of it, it's a plus 1. This is more concentrated. This is less concentrated and less concentrated. Less concentrated with hydrogen ions. pH is measured with a properly calibrated pH meter. Okay, it is said that these figures are easier to work with than the actual Ka values. So the P of the Ka, the power of the Ka, is more easy to interpret than the actual Ka. Okay, now to the trained eye, that is. So basically, look at again. I'm picking on the 10 to the minus 10. This is the lowest concentration, but yet it's got the highest power in the pKa. The 10 to the, let's go this way, 10 to the, okay, 10 to the minus 4 is the highest concentration that we have here, 10 to the minus 4, but yet it's got a lower pKa. So this is down to interpretation, and you have to be able to read these tables. That's important. Okay, we've got a nice ice problem right here, okay? That's a nice ice problem, and what that means is that we've got to look at our initial concentrations, we've got to look at our change in concentration, and finally we have to look at our equilibrium concentration, okay? So we have our reactants here. This is our reactant concentration, governed by the equation right here. We're doing a strike off of H2O. We're not concerned with that. That's got a value of 1. Has no effect once we go for our equilibrium constant equations. Strike it off. These are on the right hand side. These are on the formation side of the reaction, starting off with the values of 0 and 0 in concentration, changing to a plus x as they change, and in equilibrium they end up as x molar and x molar, as opposed to the initial concentration of reactants reduces from 0.25 minus the x value. Okay, now what else is in this question? Well, we were given the pH already, okay? So this is going to aid us then in working out our actual value. Okay, and you've got to ask yourself then, why is the pH important in this? We've got a pH of 2.72. pH is important because, remember, the reverse of pH brings us back to the actual concentration, okay? So a plus 2.72 means that we came from a concentration of 10 to the power of minus 2.72. Remember that? That's how it works. So that links into our concentration right here of H3O. pH, hydrogen ion concentration, is hydronium concentration. And that has ended up as being X. So therefore, X has a pH of 2.72, so we'll be able to work out our concentration then. Okay, exactly as I said then, pH equals minus log of the hydrogen ion concentration. Get right to it. Minus log we've got to switch the negative, we've got to switch the anti-log, or the log over becomes an anti-log. H3O, and this is actually the way it goes into your, when you do the anti-log in your calculator, you've got your anti-log function is directly above the log function, and it's a 10 to the x, okay, and that's what you type in when you want to get the anti-log. You will have the negative on this side, and on your calculator type in the 10 to the power of, and then type in negative 2.72. Shoot an equals, and you're going to get 1.9 by 10 to the minus 3 as your concentration for the hydrogen ion concentration. You can trust me, that's the case. Attempt it yourself and see what happens. It'll work. So at this point you've got the hydrogen. So this means we've got X then, okay? So in our equation then, our dissociation constant equation, we've got our formation products up above, we've got our reactants underneath. We now know this concentration here, H3O. This one, if you look back, let me just show it again. So these two both had X molarity concentration, okay, X molarity concentration. So your upper line is just going to be X by X, which happens to be now 1.9 by 10 to the minus 3, and that's squared. Oh yeah, here's your X by X, and underneath you've got your 0.25 minus X. In any case, X is 1.9 by 10 to the minus 3, squared off, and underneath you've got 0.25 minus 1.9 by 10 to the minus 3. Plug and chug, and answer for constant of dissociation is 1.5 by 10 to the minus 5. And there you go, that fits in pretty well with our typical pKa values and Ka values for weak acids and weak bases. So these figures match up. The 10 to the minus 5 that we just got fits the empirically established values. So that's good to go. In calculating pH values of solutions of weak acids, use Ka expression to calculate the hydrogen ion concentration, and then once you've got that, you calculate pH from the hydrogen ion concentration. Calculate pH values of solutions of weak bases. Use Kb expression to calculate OH minus concentration. Calculate pOH from that, and then simply pH is equal to 14 minus pOH. And this will give you the hydrogen ion, or the pH value. And again, then there you see the graphic. Got the idea that as Ka and hydrogen ion concentration increase, pH when you calculate it actually appears to be a low number. It is a low number, but a low number pH corresponds to a high hydrogen ion concentration. Increase in base strength. Again, as the hydrogen ion decreases, well, let's see, as the Kb and the pH increase, the hydrogen ion decreases. And that kind of makes sense because this is the dissociation constant for a base, and if this value increases, it means that you're a lot more basic, which means you're going to have less hydrogen ion concentration. And similarly, as pH increases, this is the let's see, pH increasing means that you're going up from the zero. Now zero is, remember, a strong acid, which means there's a lot of hydrogen and protons. But as it goes up, it increases. It means that you've got less of the hydrogen ion concentration. Okay, I hope the video helps a little bit. Look forward to making the next one. Enjoy making this one as well. Talk to you then.